So in our last lesson, we looked at the relationship between rate and concentration. So anytime you're comparing the rate of a reaction with the concentration of one of the substances involved in the reaction, we use our rate laws or rate law expression. Rate equals K times concentration of whatever. But what if we are asked to compare, say, concentration to time? So not concentration to rates, but concentration to time. I mentioned earlier to be careful about the time it takes for a reaction to occur versus rate. They are related, but they are definitely not the same. So anytime we're comparing concentration to time, we're going to use some more equations known as the integrated rate laws. So as the name implies, these are derived from using calculus. In fact, there's some pages in your textbook that go through the derivations of the integrated rate equations on 626 to 628, I believe. So if you're in calculus and you're interested where these equations we're about to see came from, then go ahead and take a look there. If you're not interested, like me, then don't worry about it and we'll just learn how to use them. All right, so it says in reactions, it is sometimes useful to obtain answers to the following two questions. How long must a reaction proceed in order to reach a specific concentration of some reactant? So you start off with 1 molar of a substance. How long does it take to get to 0.3 molar? So we can answer that question using one of the integrated rate equations. Or what will be the concentration of one of the chemicals after a specific amount of time has elapsed? So you start off with this amount, you let the reaction go for 10 minutes. What will the concentration of this substance be after that time? So these are the two main types of questions that we can answer using the integrated rate equations. Now, just to warn you, there are different equations for different reaction orders. So we're just going to look at zero order, first order, and second order. Third order reactions are extremely uncommon. We'll talk about why that's the case when we get into the relationship between, say, the collision theory and a rate law. And so most reactions are either first or second order, though there are some zero order reactions as well. So let's start off with zero order. Now, also something to be aware of on your reference sheets, your advanced placement chemistry equations and constant sheets, there's two of the three integrated rate equations given to you, and they're in a little bit different form. So let me show you the difference. All right, for zero order reactions, we get this rate equation. A naught concentration of, we'll just call it substance A, concentration of A naught minus concentration of AT equals KT. Now note too, your book uses AKT, where A is the coefficient from the chemical equation, and your book is literally the only place that I have ever seen this. So we're just going to stick with this form. In fact, this is similar to what's on your equation sheet, except zero order is not on there. So just make sure you know that. So A naught is the initial concentration of some substance. AT is a concentration of some substance after the elapsed time T. And then K is your rate constant, just like from your rate law expression. All right, first order. So if you have a first order reaction, first order overall, first order in a particular substance, we'd use this equation. So this is different than what your equation sheet shows. Your equation sheet shows the difference between the natural log of the initial concentration and concentration after some time. The ratio, natural log of the ratio, is the same as the difference in the natural log. So we'll just go with this form. So that's ln, natural log. So natural log of the initial concentration over the concentration at time t, and again, we have equal to K and T. Something else that's very useful is to determine what's called the half-life of a reaction. So if you recall, that's T 1/2. That kind of looks funky there, but T 1/2 is the symbol we use for half-life. Half-life is a rate. Half-life represents the time it takes for half of a substance to react. So we talked about half-lives with uh, radioactive decay processes, for example, but it applies to any chemical reaction. So how long does it take for half of the reactant to be consumed? Well, let's think about this. We can derive it because I don't want you to just memorize the formula for half-life, and let's derive it. So let's say you start off with, oh, I don't know, let's say you start off with 10, whatever, doesn't matter. So how much is left after time t? Well, you get 5. So really, we go natural log of 2 equals kT, where t is our half-life. And so if we rearrange that, well, what is the natural log of 2? The natural log of 2, go ahead and type that into your calculator, see what you get. So we end up with an equation that looks like this, 0.693 over k. So all we need to know is the rate constant. Take 0.693, which is natural log of 2, over the rate constant, and that'll give us um, the time that it takes for half of the reactants to be consumed. So again, this is a very useful. You can, sometimes it's kind of hard to tell in the problem because they don't give you any values for A naught and AT. Just know that it's half, so we're taking natural log of 2. All right, second order, we get this, the inverse of the concentration of AT. So it's different order than last time, so be careful. Minus 1 over A naught equals KT. So going back to kind of trying to remember all of this stuff, zero order, it's just concentrations, difference in concentrations. Be careful, it's A naught minus AT. First order, we got natural log of A naught minus natural log of AT, or natural log of A naught over AT. And then second order, inverse AT minus A naught. So pick the appropriate equation depending on the order of the reaction. All right, let's do this. Let's do some practice with using one of these integrated rate equations. There's not really room in your notes. I apologize for that. So maybe the top of that page or the bottom of the page underneath first order reactions. Let's do number 33. That's in the back of the book, or in the back of the chapter. This is on page 653. So go ahead and read along with me, please. The second order rate constant for the following gas phase reaction is 0.0442 per molar second. Now, sometimes it doesn't tell you the order of the reaction, and it'll just give you the rate constant. We talked about the units of the rate constant the other day, and so you may need to recognize, 0.0442 per molar second. Only a second order reaction is going to have units for K as per molar second. So remember, first order would just be per second, per time. So second order per molar second. So we start with 0.135 moles of C2F4 in a 2-liter container with no C4F8 initially present. All right, so first question, what will be the concentration of C2F4 after 1 hour? So let's start with this. Let's go ahead and determine the concentration, initial concentration of C2F4. Go ahead and pause the video and get that value in moles per liter or molar. Molar is fine. I'm not too worried about sig figs here in this problem. I just want to focus on the process first. So we have an initial concentration of 0.0675 molar. So this is second order reaction overall. And so we're trying to find the concentration after some elapsed time. So we're looking for, and we'll just write A is fine, or X, it doesn't really matter, or C2F4 is technically what it is. So let's plug in our values. So 0.0675. Our rate constant 0.0442 per molar second. And we're going to multiply that by the elapsed time. Now notice something. Look at what it says in the question and look at our units in our rate constant. So the elapsed time is 1 hour, but in our rate constant, the units are seconds. So we need to convert that 1 hour to seconds, which is 60 times 60, 3,600 seconds. All right, so you may want to multiply those two first, and then we're going to, whatever this value here is 1 over 0.0675, we're going to add that to the other side, remember, because it's a minus here. And then we have 1 over AT equals whatever's on that other side. Go ahead and pause the video and punch this up and see what you get. All right, so hopefully you got this answer. 0.00575 is how much we have after 1 hour. Take a look, letter B. What will be the concentration of the product after 1 hour? So now this one's a little bit trickier. So I'm going to make kind of a SCAR table to help guide us through this calculation, because it's actually more complex than you think. So this is how much of C2F4 is left after an hour. So we need to find out how much reacts. And then once we know how much reacts, we can use that to find out how much product forms. So let's take a look at our equation. So we have 2C2F4 is going to make C4F8. And so we started off with how much? And it's not really after the reaction, it's after some point in the reaction. So we can use molarity here, or you can use moles. Either way is fine. I'm going to use molarity since we have that value. So remember, we started with 0.0675 molar. That's what we said was our A naught. And then how much do we have after, how much is reacts? We don't know that yet, but we do know how much is left after 1 hour, which is 0.00575 molar. So of course that's going to go down. There's none of that. That's going to go up. So we need to figure out how much the concentration decreased by. Go ahead and pause the video, find that number. I'm not worried about sig figs here. All right, so it looks like the concentration went down by 0.0618 or 0.6175. Either way is fine. So how much is the concentration of the C4F8 going to go up by? Here's where we use our stoichiometry. So C4F8 is going to go up by half the amounts that the C2F4 goes down by. So I'll just type it in like this. Whoops, is that 6175? And then that'll give us this concentration right here. Go ahead and do that. Pause the video now, please. All right, so it looks like we have a concentration after 1 hour of 0.0308 molar for the C4F8. All right, let's try letter C. What is the half-life of the reaction for the initial C2F4 concentration given in part A? So we can't, first of all, this is not first order reaction, so we're not going to do 0.693 over K. Second of all, we're not just going to put AT as being half of A naught. We're actually going to use the values. So let's again take a look. Let me set this up with some numbers for you. So using the integrated rate equation for second order reaction, 1 over AT minus 1 over A naught equals KT. Recall that our initial concentration is 0.0675 molar. So we want the half-life, so we want to know how long it takes for half of that to react. And so we're going to take half that value, which is 0.03375. Again, I'm not too worried about sig figs here at the moment. So that is half of our original concentration is equal to K, which if you recall was 0.0442 per molar second times T. And so we're going to solve for T, that being our half-life. Go ahead and pause the video, do that now. So I got different answers here in my notes, so we'll have to check and see which one is right. So I think it is 265 seconds. But for some reason in my notes, I also have written 335 seconds, but I don't have any work to support that, so I'm not exactly sure where that came from. So hopefully we got the right answer here. 265 seconds or 4.42 minutes. Just depending on what we're asked to find the time in. All right, one more, letter D. How long will it take for half of the C2H4 that remains after 1 hour to disappear? So again, each half-life is the time it takes for half of that substance to disappear. And so every 265 seconds, half of what you had will disappear. So it's going to take 265 seconds for half of whatever you had after 1 hour to be consumed as well. In some situations, you may be given a graph of some experimental data, and from that graph, determine reaction order and to determine the rate constant. So take my word for it. It says the rearranged forms of each of the 3 above equations can all be shown to take the general formula of y equals mx plus b format, slope-intercept form. So if a reaction is 0 order, if we plot the concentration versus the time, we're going to get a graph that looks like this. We get a straight line with a negative slope, and the significance of that slope is that it is the negative of our rate constant. So the slope is negative, so just take the positive of that negative slope, and that'll give you the rate constant. So actually, I think I'm going to write it this way. The negative of the slope equals our rate constant. That might be better, I think. Either way, same thing. So concentration, if the plot of concentration versus time yields a linear graph with a negative slope, that means that the reaction is 0 order for that substance, and the rate constant is simply the negative of the slope. All right, first order reaction. Any guesses what's going to yield a straight line? This time we have the natural log of concentration. Let's see if I can squeeze that in there. Natural log of concentration versus time. This plots, again, we got a linear graph there. So if a plot of natural log of concentration of a substance versus time is linear with a negative slope, that means the reaction is first order in that substance. Once again, the negative of the slope will give us our rate constant. All right, one more. Again, hopefully you can figure this one out. Any guesses of what plotting of what variables will give us a straight line? If it's a second order reaction, you got it. Inverse of concentration versus time. Be careful this time, we get that. So our rate constant will be simply the slope. So again, depends on what you're given. In fact, take a look in the book on page 629. It goes over the different types of graphs. And in fact, it gives some data. So if you look in about the middle of the page there, it gives the times for the reaction, and then the concentration at each of those times, 0 minutes, 2 minutes, 4 minutes. And then you can calculate the natural log of concentration. Notice there, initial concentration 2 molar, and the natural log of that, 0.693. I can do inverse, so 1 over 2, of course, is 0.5. And so again, kind of the same thing. If you look through that example, trying to determine the order of the reaction by graphing the data. This is something that you'll have to do in our next lab. So make a plot of concentration versus time, make a plot of natural log of concentration versus time, and make a plot of inverse of concentration versus time. So again, what we're looking for here is the graph that is linear. And that linear graph then will help us to determine the order of the reaction. So first graph, concentration versus time, is not linear. So that means this reaction is not 0 order. Just below that, inverse of concentration versus time, also not linear. So it's not second order. And then to the left of that, natural log of concentration versus time is linear. And so that tells us that this reaction is first order. Again, we can take the slope of that line, and that will give us our rate constant, which we can use to do all kinds of different calculations. Be aware that the slope is always the rate constant. This is on the next page in your notes. It's not on the slide though, so just want to warn you about that. The slope is always the rate constant. Again, for zero and first order reactions, it is the negative slope that is the rate constant. Your rate constant is always going to be a positive value. All right, that concludes this lesson. We will continue next time with the collision theory. Thanks for watching.